Welcome to this coding walkthrough. Today, we'll be solving LeetCode problem number 2097, titled Valid Arrangement of Pairs. This is an exciting problem where we'll explore graph algorithms to find a valid sequence of directed edges. Let's dive in and break it down step by step. In this problem, we are tasked with finding a valid arrangement of pairs. Each pair is represented as a directed edge, where pairs I equals A underscore I, B underscore I, indicates a directed edge going from node A underscore I to node B underscore I. A valid arrangement means that for every consecutive pair in the sequence, the second element of one pair, B underscore I, must match the first element of the next pair, A underscore I plus 1. Additionally, all pairs must be used exactly once, though they can appear in any order as long as the arrangement satisfies these conditions. If there are multiple valid arrangements, we can return any one of them. The input we receive is a list of pairs, and the output should be a valid arrangement of those pairs as a sequence. The problem ensures that a valid arrangement always exists, so we don't need to handle cases where it's impossible to create such an arrangement. To better understand the problem, let's look at an example. Suppose the input is pairs equals 5, 1, 4, 5, 11, 9, 9, 4. One possible valid arrangement of these pairs is 11, 9, 9, 4, 4, 5, 5, 1. This arrangement works because the second element of each pair matches the first element of the next pair. Specifically, 11 leads to 9, 9 leads to 4, 4 leads to 5, and finally 5 leads to 1. Additionally, all pairs are used exactly once, satisfying the problem's requirements. This demonstrates how the pairs can be rearranged into a sequence that forms a valid arrangement. Now, consider another example where the input is pairs equals 1, 3, 3, 2, 2, 1. A valid output for this input is 1, 3, 3, 2, 2, 1. Here, the sequence works because 1 leads to 3, 3 leads to 2, and 2 leads back to 1. Once again, all pairs are used exactly once, and the condition that the second element of one pair matches the first element of the next is satisfied. This example highlights that the arrangement doesn't necessarily require any reordering if the input already forms a valid sequence. In a third example, consider the input pairs equals 1, 2, 1, 3, 2, 1. One possible valid arrangement is 1, 2, 2, 1, 1, 3. In this arrangement, 1 leads to 2, 2 leads back to 1, and 1 leads to 3. This sequence satisfies all the conditions of the problem. It's worth noting that this input allows for multiple valid arrangements, as the pairs can be reordered in different ways while still forming a valid sequence. The key takeaway is that as long as the conditions are met, any valid output is acceptable. Finally, let's review some important constraints and edge cases. The problem guarantees that the input size can go up to 100,000 pairs, so the solution must be efficient, ideally with a time complexity better than n squared. In edge cases, such as having only one pair, the output is simply the input itself since there are no other pairs to arrange. The problem also ensures that the graph formed by the pairs will always allow for a valid arrangement, so we don't need to handle disconnected graphs. Additionally, since multiple valid outputs are possible for some inputs, any arrangement that meets the criteria can be returned. This flexibility allows us to focus on finding one valid solution rather than all possible ones. To solve problem number 2097, the goal is to find an arrangement of pairs such that the last node of one pair matches the first node of the next, while using all pairs exactly once. This challenge can be framed as constructing an Eulerian path in a directed graph. A brute force method for this would involve generating all permutations of the pairs and checking if any sequence satisfies the condition. While this approach is simple in theory, it quickly becomes computationally infeasible due to its factorial time complexity. For example, with just 10 pairs, the number of permutations to evaluate would already be in the millions. Instead, we turn to graph theory for a more efficient solution. Specifically, we leverage the concept of an Eulerian path, which is a trail in a graph that visits every edge exactly once. For a directed graph to have an Eulerian path, 3 key properties must hold. At most one node can have an outdegree greater than its indegree, at most one node can have an indegree greater than its outdegree, and all edges must belong to the same connected component. By reframing the problem in this way, we can utilize well-established algorithms to find a solution efficiently. Given this understanding, we can break the solution into clear steps. First, we construct a directed graph from the input pairs, where each pair, A, B, represents a directed edge from node A to node B. Next, we calculate the in-degree and out-degree for each node to identify potential starting and ending points for the Eulerian path. Once the graph is prepared, we apply Heyerholzer's algorithm to construct the path. This algorithm starts from a node with out-degree greater than in-degree, if such a node exists. From there, we perform a depth-first traversal while maintaining a stack to track the nodes visited along the path. When we backtrack, we add nodes to the final path. Once the traversal is complete, the stack contains the Eulerian path in reverse order. By reversing the stack, we obtain the valid sequence of pairs that meets the problem's requirements. This approach not only ensures that all edges are used exactly once but also guarantees that the sequence respects the constraints of the problem. This approach is chosen for several reasons. First, it guarantees correctness by directly leveraging the mathematical properties of Eulerian paths. Second, it is computationally efficient, running in O(E) time, where E represents the number of edges or pairs. This makes it scalable to large inputs, unlike the brute force method, which suffers from exponential time complexity. While the Eulerian path method does involve additional steps like graph construction and degree calculation, these are straightforward and necessary to achieve optimal performance. Alternative methods, such as simple breadth-first or depth-first search, may traverse the graph but fail to guarantee the correct ordering of edges, making them unsuitable for this problem. In contrast, the Eulerian path approach aligns perfectly with the problem's constraints and ensures all pairs are used exactly once in the correct order. By using Heyerholzer's algorithm, we achieve a solution that is both elegant and efficient, making it the ideal choice for this problem. In this problem, we are tasked with finding a valid arrangement of pairs such that the sequence forms a valid path in a directed graph. The key requirement is that the last node of one pair must match the first node of the next pair, and all pairs must be used exactly once. This brings us to the concept of an Eulerian path, which is a trail in a graph that visits every edge exactly once. Solving this problem involves three main steps. First, representing the graph using adjacency lists. Second, verifying that the graph satisfies the necessary conditions for an Eulerian path. And third, constructing the path using a depth-first search-based algorithm. By breaking it into these components, we can systematically approach the solution and ensure that all constraints are met. The first step in solving the problem is to represent the graph. We use an adjacency list, which is a dictionary where each key represents a node, and the value is a list of nodes to which it has outgoing edges. Alongside this, we maintain in-degree and out-degree counts for each node. These counts help us verify the conditions for an Eulerian path. Next, we check the Eulerian path conditions. For such a path to exist in a directed graph, there are three key criteria. First, the number of nodes with out-degree greater than in-degree must be at most 1, this will be the starting node of the path. Second, the number of nodes with in-degree greater than out-degree must also be at most 1, this will be the ending node. Finally, for all other nodes, the in-degree and out-degree must be equal. By traversing the degree counts, we can identify whether these conditions are satisfied and determine the starting node if one exists. After verifying the conditions for an Eulerian path, we move to constructing the path itself using a variation of Heyerholzer's algorithm. This algorithm is specifically designed for finding Eulerian paths efficiently. The process begins by starting the depth-first search from the node with out-degree greater than in-degree, if such a node exists. If no such node exists, we can start from any node with edges. As we traverse the graph, edges are removed once they are visited, this ensures that no edge is revisited. A stack is used to manage the traversal dynamically, allowing us to explore new edges while keeping track of nodes whose edges are yet to be fully processed. Once all edges from a node have been used, we pop it from the stack and finalize it as part of the path. Since this traversal builds the path in reverse order, we reverse it at the end to get the correct sequence. Finally, the sequence of pairs is reconstructed from the path by iterating through consecutive nodes. There are several key insights that help us solve this problem effectively. First, the adjacency list representation is not only space efficient but also allows for quick traversal and edge removal during the DFS. Second, verifying the degree conditions is critical to ensuring that a valid Eulerian path is possible, as these conditions guarantee that the graph structure supports such a path. Identifying the starting node based on these conditions is essential for the correctness of the algorithm. Third, Hierholzer's algorithm is optimal for constructing Eulerian paths, operating in linear time relative to the number of edges. Additionally, removing edges during traversal ensures that no edge is revisited, which is crucial for maintaining correctness. Lastly, since the path is constructed in reverse during the DFS, reversing it at the end gives us the correct order for output. To implement this algorithm, we rely on a few key data structures. The adjacency list is a dictionary where keys represent nodes, and values are lists of nodes they point to. This allows us to efficiently traverse and modify the graph. Degree counts are maintained in two dictionaries, one for in-degree and one for out-degree. These are used to verify Eulerian path conditions and identify the starting node. A stack is employed during the DFS to dynamically manage the traversal and ensure edges are processed in the correct order. Finally, a result list is used to store the constructed path in reverse, which is later reversed for the final output. In terms of complexity, the algorithm is highly efficient. The time complexity is O, V plus E, where V is the number of nodes and E is the number of edges. This accounts for both graph construction and the DFS traversal. The space complexity is also O, V plus E, as we need space for the adjacency list, degree counts, and stack. Let's walk through an example to see how the algorithm works. Suppose we are given the input pairs 1, 3, 3, 2, 2, 1. First, we represent the graph using an adjacency list 1, 3, 3, 2, 2, 1. The in-degree and out-degree for each node are also calculated 1, 1, 3, 1, 2, 1 for both. Next, we check the Eulerian path conditions. Here, all nodes have in-degree equal to out-degree, which means a valid Eulerian path exists. We can proceed with the DFS traversal. Starting from node 1, we traverse the edges in the order 1-3-2-1. As we visit each edge, it is removed from the graph, and the traversal builds the path in reverse order 1, 2, 3, 1. Finally, we reconstruct the sequence of pairs from the path. The path we constructed in reverse order was 1, 2, 3, 1. Reversing this gives us the final order of nodes, from which we derive the sequence of pairs 1, 3, 3, 2, 2, 1. This is the output of the algorithm, which satisfies all the problem constraints. Each pair connects seamlessly to the next, forming a valid Eulerian path, and all pairs are used exactly once. This concludes the solution, demonstrating how the graph representation, degree checks, and Hierholzer's algorithm work together to solve the problem efficiently. Here, we start by importing the necessary modules. We use defaultDict to simplify the creation of our adjacency list in degree maps, and Deque for efficient edge removal during traversal. The valid arrangement function begins by constructing the graph representation and calculating the in-degrees and out-degrees for each node. For every pair in the input, we add the destination node to the adjacency list of the source node. Simultaneously, we increment the out-degree of the source and the in-degree of the destination. This helps us track the balance of edges entering and leaving each node, which is critical for determining the starting point of our Eulerian path. Next, we locate this starting node. By default, we choose the first node of the first pair, but if we find a node with more outgoing edges than incoming edges, that becomes the new starting point. This ensures that we begin the traversal in a way that satisfies the conditions of an Eulerian path. Finally, we define a helper function, find_Eulerian_path, to perform the actual traversal. It initializes a stack with the starting node and prepares to iteratively build the path. The find_Eulerian_path function completes the graph traversal using Hierholzer's algorithm. While the stack isn't empty, it continues to explore the graph. For the current node at the top of the stack, if it has remaining outgoing edges, the algorithm moves to the next node by popping an edge from the Deque and adding the destination node to the stack. If there are no outgoing edges left, it means this node's traversal is complete, so it gets added to the final path and removed from the stack. Once the traversal is complete, the path is reversed to correctly reflect the Eulerian path order. Now, the solution moves to the final step, converting the Eulerian path into the required arrangement of pairs. By iterating through consecutive nodes in the path, it reconstructs the edges as pairs and appends them to the result list. This result represents a valid arrangement of the input pairs and is returned as the output of the function. To solve the valid arrangement of pairs problem, we start by building the adjacency list and calculating the in-degrees and out-degrees for each node. The adjacency list is stored as a hash map where each key represents a node, and its value is a deque containing all the nodes it points to. As we iterate through the input pairs, we add each connection to the graph. For example, if a pair is U, V, we ensure that U has an entry in the graph and append V to its list of neighbors. At the same time, we maintain two additional maps, one for the out-degree of each node, which counts how many edges originate from it, and another for the in-degree, which tracks how many edges point to it. After constructing these maps, we need to determine the starting node for our Eulerian path. The key property here is that if a node has a higher out-degree than in-degree, it must be the starting point. By default, we initialize the starting node as the first node in the input pairs, but we update it if we find a node that satisfies this property. Once the starting node is determined, we proceed to construct the Eulerian path using Heyerholzer's algorithm. Now, we implement Heyerholzer's algorithm to find the Eulerian path. This is done using a helper method called findEulerianPath. Starting from the designated node, we recursively traverse the graph, removing edges as we visit them. For each node, we take its list of neighbors from the adjacency list and process them one by one. If there are no more neighbors left to visit, the current node is added to the path. By the end of this process, the path is built in reverse order, so we use collections.reverse to correct it. Once the Eulerian path is constructed, we convert it into the required format. Each edge in the path becomes a pair in the result array, where the first element is the starting node of the edge, and the second element is the ending node. Finally, the result array is returned, providing a valid arrangement of the input pairs. To solve this problem, we start by building an adjacency list and calculating the in and out degrees for each node. Looking at the pairs 1, 3, 3, 2, 2, 1, we process each pair one by one. For 1, 3, we add 3 to the adjacency list for node 1, increment the out degree of node 1 to 1, and increase the in degree of node 3 to 1. Next, 4, 3, 2, we add 2 to the adjacency list for node 3, update its out degree to 1, and increase the in degree of node 2 to 1. Finally, 4, 2, 1, we add 1 to the adjacency list for node 2, update its out degree to 1, and increase the in degree of node 1 to 1. By the end of this step, the adjacency list is 1, 3, 3, 2, 2, 1, and both the in degrees and out degrees of all nodes are balanced at 1. Since no node has an out degree greater than its in degree, we can choose node 1 as the default starting node. To find the Eulerian path, we use Heyerholzer's algorithm. Starting at node 1, we initialize the stack with 1 and keep an empty path. From node 1, we pop 3 from its adjacency list and add it to the stack, updating the stack to 1, 3. From node 3, we pop 2, adding it to the stack, which becomes 1, 3, 2. From node 2, we pop 1, updating the stack to 1, 3, 2, 1. At this point, node 1 has no more edges, so we begin backtracking. We pop 1 from the stack and add it to the path, which is now 1. We continue backtracking, popping 2 to make the path 1, 2, then 3 to make it 1, 2, 3, and finally 1 to complete the path as 1, 2, 3, 1. Reversing this path gives 1, 3, 2, 1, which is the Eulerian path. Converting this path into consecutive pairs, we get 1, 3, 3, 2, 2, 1, which is the valid arrangement. In this example, we are given the pairs 1, 2, 2, 3, 3, 1, 3, 4. The first step is to build the adjacency list and calculate the in and out degrees for each node. For 1, 2, we add 2 to the adjacency list of node 1, incrementing the out degree of node 1 to 1 and the in degree of node 2 to 1. For 2, 3, we add 3 to the adjacency list for node 2, updating its out degree to 1 and the in degree of node 3 to 1. For 3, 1, we add 1 to the adjacency list for node 3, updating its out degree to 1 and the in degree of node 1 to 1. Finally, 4, 3, 4, we add 4 to the adjacency list of node 3, increasing its out degree to 2 and the in degree of node 4 to 1. At the end of this step, the adjacency list is 1, 2, 2, 3, 3, 1, 4, and the indegrees and outdegrees are 2, 1, 3, 1, 1, 1, 4, 1, and 1, 1, 2, 1, 3, 2, respectively. Here, node 3 has an outdegree greater than its indegree, so it becomes the starting node. Using Hierholzer's algorithm, we started node 3 with the stack initialized as 3, and the path as an empty list. From node 3, we pop 1 from its adjacency list and add it to the stack, which becomes 3, 1. From node 1, we pop 2, updating the stack to 3, 1, 2. From node 2, we pop 3, making the stack 3, 1, 2, 3. From node 3, we pop 4, updating the stack to 3, 1, 2, 3, 4. At this point, node 4 has no more edges, so we backtrack by popping 4 to the path, making it 4. Continuing to backtrack, we pop 3 to get 4, 3, then 2 to get 4, 3, 2, then 1 to get 4, 3, 2, 1, and finally 3 to complete the path is 4, 3, 2, 1, 3. Reversing this path gives 3, 1, 2, 3, 4, which is the Eulerian path. Pairing consecutive nodes, we get 3, 1, 1, 2, 2, 3, 3, 4, which is the valid arrangement. In this example, we are given the pairs 1, 2, 2, 1. We start by building the adjacency list and calculating the in and out degrees. For 1, 2, we add 2 to the adjacency list for node 1, incrementing the out degree of node 1 to 1 and the in degree of node 2 to 1. For 2, 1, we add 1 to the adjacency list for node 2, updating its out degree to 1 and the in degree of node 1 to 1. At the end of this step, the adjacency list is 1, 2, 2, 1, and both the in degrees and out degrees of all nodes are balanced at 1. Since no node has an out degree greater than its in degree, we can choose node 1 as the default starting node. Using Hierholzer's algorithm, we started node 1 with the stack initialized as 1 and the path as an empty list. From node 1, we pop 2 from its adjacency list and add it to the stack, updating the stack to 1, 2. From node 2, we pop 1, updating the stack to 1, 2, 1. At this point, node 1 has no more edges, so we backtrack by popping 1 to the path, making the path 1. Continuing to backtrack, we pop 2 to get 1, 2, and finally pop 1 to complete the path as 1, 2, 1. Reversing this path gives 1, 2, 1, which is the Eulerian path. Pairing consecutive nodes, we get 1, 2, 2, 1, which is the valid arrangement. To understand the time complexity of this problem, let's break it down step by step. First, when building the graph, we iterate through the pairs array, which contains n pairs. For each pair, u, v, we add v to the adjacency list of u and update the in degree and out degree for the nodes. Since this involves a single pass through the pairs array, this step takes n time. Next, we need to find the starting node for the Eulerian path. This requires iterating over all unique nodes. There are at most 2n unique nodes because each pair contributes 2 nodes. Checking the in degree and out degree for each node is a constant time operation, so the total time for this step is 2n, which simplifies to n. Now, let's analyze the time complexity of finding the Eulerian path using Hierholzer's algorithm. This is done through a stack-based iterative DFS. In this approach, each edge is visited exactly once and removed from the adjacency list using dec.popleft, which is an O1 operation. Since there are n edges in total, this step takes n time. After constructing the Eulerian path, we then need to process it into the final result. The Eulerian path contains exactly n plus 1 nodes, and converting it to the required pairs involves a simple iteration, which also takes n time. When we sum up the time complexities for all steps, building the graph, finding the starting node, performing the DFS, and constructing the result, we arrive at an overall time complexity of n plus n plus n plus n, which simplifies to n. Shifting our focus to space complexity, the algorithm also demonstrates efficiency. The adjacency list used to represent the graph is stored as a dictionary, where each key maps to a deque of neighbors. Since there are at most n edges and 2n nodes, the space required for the graph representation is n. Additionally, we use hash maps to store the in degree and out degree of each node. These hash maps require space proportional to the number of unique nodes, which is also n. During Heyerholzer's algorithm, the DFS stack size is proportional to the number of edges, which is O, n, and the Eulerian path, which contains n plus 1 nodes, also takes O, n, space. Combining all these contributions, the total space complexity is O, n, plus O, n, plus O, n, which simplifies to O, n. To highlight the difference between a brute force approach and the optimized solution, let's compare their complexities. A naive approach would involve generating all possible permutations of the pairs array to find a valid arrangement. This results in a factorial time complexity, O, n, which becomes impractical even for moderately sized inputs. In contrast, the current solution leverages Heyerholzer's algorithm, designed specifically for efficiently finding Eulerian paths. By visiting each edge just once, the time complexity is reduced to O, n, which is a dramatic improvement. Importantly, this O, n, complexity holds true for the best, average, and worst cases, as the algorithm always processes the graph in a linear number of steps relative to the edges. Finally, let's validate the O, n, time complexity mathematically. Each edge in the graph is visited exactly once during the DFS traversal in Heyerholzer's algorithm, ensuring that this step is linear in time. Additionally, the other operations, such as building the graph, identifying the starting node, and converting the Eulerian path into the result, are all simple iterations over nodes and edges. These operations are also linear with respect to the size of the input. Therefore, by summing these linear contributions, we can confidently conclude that the algorithm runs in O, n, time, where n represents the number of edges in the input. When solving this problem, there are several common mistakes to watch out for. First, it's easy to overlook the Eulerian path requirements. Remember, for a graph to support an Eulerian path, the in-degree and out-degree of nodes must differ by at most 1. If this condition isn't adhered to, the graph simply cannot have a valid arrangement, leading to incorrect results. Another frequent issue arises when handling disconnected graphs. If your solution doesn't ensure that all edges belong to the same connected component, it can fail, as disconnected components make it impossible to construct a valid path. Additionally, errors in implementing Heyerholzer's algorithm can be tricky. For instance, failing to backtrack properly during the depth-first search can result in incomplete or invalid paths. Always make sure to append nodes to the path after recursion has completed, rather than during the traversal itself. A less obvious but critical mistake is failing to traverse all pairs exactly once. This often happens when the graph traversal isn't designed carefully, leading to edges being skipped. Finally, edge cases like graphs with only 1 or 2 edges are easy to overlook. Testing thoroughly with small inputs is essential to avoid runtime errors or unexpected behavior. Now, let's consider some key insights for interviews. Recognizing the pattern is crucial. This problem is a classic application of finding an Eulerian path in a directed graph. Problems involving Eulerian paths often appear in graph theory interviews, so understanding the fundamentals will give you an edge. For optimization, Heyerholzer's algorithm is your best tool, allowing you to construct the path efficiently in O, e, time, where e is the number of edges. This is both optimal and elegant. During interviews, it's also important to effectively communicate your approach. Be ready to explain why the Eulerian path conditions apply here and how your algorithm ensures that all pairs are used exactly once. Test cases are another area to focus on. Interviewers often challenge candidates with edge cases, such as disconnected nodes or graphs containing cycles. Being able to systematically address these scenarios demonstrates a solid understanding. Finally, it's helpful to connect this problem to related ones. For example, LeetCode 332, Reconstruct Itinerary, is another Eulerian path problem. Similarly, problems like LeetCode 210 and 207, dealing with course schedules, involve directed graphs, while LeetCode 399 explores graph traversal for evaluating division. Drawing these connections can help you see the broader applications of these concepts. Let's explore some alternative approaches for this problem. One method is using backtracking with depth-first search to generate all permutations of pairs and check their validity. While this brute force approach is conceptually simple, it's highly inefficient due to its O, n, complexity, making it impractical for larger inputs. The trade-off here is simplicity versus scalability. A much better option, and the optimal approach, is Heyerholzer's algorithm. By directly constructing the Eulerian path, this method ensures all edges are traversed in O(e) time, where e is the number of edges. While it requires a solid understanding of Eulerian paths and careful implementation, this approach is highly efficient and tailored to the problem. Another alternative involves graph reduction with topological sorting. In certain cases, reducing the graph to a directed acyclic graph, or DAG, and performing a topological sort can simplify specific constraints. However, this method is less efficient than Hierholzer's algorithm and may not always apply to the problem at hand. Each of these approaches has its own trade-offs, but for this problem, Hierholzer's algorithm is the clear winner in terms of both efficiency and correctness. Great job following along. To wrap up, we applied graph theory concepts, specifically Eulerian paths, to solve the problem. Remember the importance of in-degree and out-degree relationships for sequence problems like this. Thanks for watching, and don't forget to like and subscribe for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!